Well, we haven't heard anything about flash welding during this symposium, so I thought maybe I would throw something in on it. But you weld things like tubing, flat sheets, solid, round, hex, square, rectangular bars. Some examples of landing gears, cooling pipes, large electrical conductors. And I guess you've already heard a lot of people talk about how you make a flash weld. You apply a voltage across two pieces to be welded. Make a light contact between the pieces, establish current through a circuit to heat the points of contact beyond melting, i.e. make it flash, and then maintain that flashing action by moving the parts, I guess at a controlled rate. There wasn't a lot talking about how to actually maintain the flashing and control what would constitute a consistent amount of flashing, because everybody dials up a flashing time and distance. But at least I haven't seen much attention paid to actually looking into what is the energy that goes into the flashing during that flashing distance, because the consistency of that is an important factor so that you have a consistent end result when you are ready to go into upset. So a lot of what I'm going to talk about is really focusing around making that happen. And then, of course, after the surfaces become sufficiently plastic, now you rapidly forge them together. So many operations doing this have high scrap rates because they can't control the flash intensity, or they can't control the flashing distance, and or they can't make a repeatable upset. And then after they do all of that, they don't have the ability to measure the results, unless they destroy it. So what they don't destroy, they really don't know how well did that perform in relation to. What they wanted to do. To make a consistent flash weld, it would seem obvious that you should use a capable machine and a capable control, make a consistent flashing intensity for consistent duration, make a consistent upset force pattern, and after you do all of that, it also helps to now verify that you had a consistent upset. So if you do all of that, so after you do a flash like that and you enter upset, you might see a pattern that looks like this, where the top pattern is the force profile. And here you could actually see that there's a resonant oscillation in the force system, because every machine has some type of specific signature response or artifact related to the way it's built, where when you really start zooming in on a small time scale, you could see different nuances that occur. What you're seeing is actually three graphs: the actual data, and then an upper limit profile and lower limit profile that's sculpted that would constitute the window that you would want to see the upset fall within for evaluation. Now verify that you had a consistent upset. Graph is the upset position. Basically, the motion is a function of time. As you're upsetting, you move in and then you end up at some upset distance. And the graph below is your velocity, where you're rapidly accelerating till you reach some peak velocity, and then as you've reached full upset, it rapidly drops down to zero. Tracking the signature response of all of those parameters together is probably the best method of verifying the repeatability of the upset process that occurred. So whatever you dial up with your machine to establish that you want, if once you enter upset, you do that type of tracking when you're done, it's a good way of verifying that you have repeatability in your process. Because if you don't have repeatability in that, then you definitely know you have a problem. In terms of a capable machine, what do you need to do that? Well, you need a sufficient transformer, voltage output to make flashing. And the typical art is to use SCR switching control wide open and select the tap ratio of the transformer to achieve the voltage that's needed for flashing. But it's really the peak voltage that's that dominates what creates that flashing. And of course, if you're making a sinusoidal shaped wave output, you're only at that peak voltage for one point in time, every 120th of a second. The rest of the time, you're at a lower voltage. So a lot of operations will see, they'll set up their arrangement like that, and then the power company has a line drop, and those are times if they're in peak demand times or brownout areas. Now they have difficult flashing, and the flashing is more intermittent that they produce. So they have a well-programmed flashing time on their control, but the energy produced is not consistent, and it intermittently turns on and off, and then that impacts what happens when they go into upset. And if they use a higher output voltage to compensate for power company line groups, things of that nature. Now they're making, when they don't have a power line drop, now you have a more intense flash than what you would normally encounter. So in short, the power company is dictating what the total energy is that's entered into your flashing. If all other variables were to remain constant, now you still have what the power company is doing to you superimposed on top of that in terms of the energy that goes into the process. So that has to affect what happens to your upset when it occurs. So if you could control that with better regulation, you've taken one variable off the table when you're grappling with everything else that you need to control during this process. So you need to move the parts together with a controlled velocity for controlled distance, then make your upset. And you also need a clamping system that's sufficient to keep the parts from slipping under the applied force during upset. We see a lot of machines that we put our equipment on where, depending on the job that they set up, the clamps actually start to slip during upset. And then on top of that, if they're really sophisticated, they might have a transducer or an LVDT or something that's measuring the final upset. And what happens is the parts start slipping in the clamps. They see that they think they achieved that upset. In fact, they think they achieved great upset when in fact they achieved undersized upset because they're seeing parts slipping in the clamps. So you really need to look at the entire profile to be able to differentiate those events and know what's really happening. And we talked a little bit about the capable control, controlling the flashing and verifying that you have the expected upset profile. And of course, it also helps if you have a control that has the ability to minimize the current demand required to control the process, because there are many flash welding installations where it puts very high current demand on the installation, and sometimes you even get in trouble with the power company over it. There are two ways you could control your flashing intensity. You could adjust the heat, or you can adjust the part feed velocity. The conventional approach people take is they have their SCR wide open, select the tap ratio to get the voltage range they want, and then they run with velocity to get the type of flashing that they have. And then they cross their fingers and hope the power company doesn't have droops that cause their flash to intermittently turn off or being run during a brownout period where they lose too much flash to be able to function. Now, with SCRs, you really can't adjust the heat too easily to adjust for flash because it's the peak voltage that dominates the flashing process. And unless you're running at in the neighborhood of 50% phase shift and lower to operate, then you're not doing anything to control the voltage. And of course, you're only hitting that voltage at one point in time. So you're dealing with something that's very inefficient in terms of producing your flashing. And once you switch to inverter technology, you could actually control that sustained peak voltage over the entire interval of flashing and control the duty cycle of that application in order to have some type of control over your flashing capability. The other method of adjusting is by adjusting the speed. If you reach a point where adjusting duty cycle is not enough to control your flashing, if you're at maximum duty cycle and you still don't have the flashing that you need, well, you need to slow your speed down. And if your part is, if you're going too fast, then you have a problem in that you also lose your ability to flash because you short out the flashing signal that you're trying to create. Well, if you're working with velocity control, you're actually responding to adjust the velocity during the process, well, then you have to integrate that with the actual machine so that you have the ability for the control to tell the machine to speed up or slow down to control the process. Now, to control the flashing intensity, you need to be able to detect the flashing intensity. And then you need the ability to increase or decrease the flashing intensity. And now you have the pieces together to be able to make this happen. But you also, if you're using velocity control, you also need to be able to detect if the loss of flashing that you're encountering is due to a loss of the electrical circuit because you're not pushing the parts together fast enough, or if it's because you're starting to create a short circuit because you're pushing them too fast. Otherwise, you don't know which direction to make the adjustment in. Now, so when it gets down to the question, how do you detect flashing intensity? Well, one obvious thing that people think of when you say, how do you detect flashing intensity, is they might say, well, just look at it. You can see how much flashing is occurring. But a camera system, conventional cameras that run at 30 or 60 hertz frame rate speeds aren't fast enough. By the time you would process and get that information, it's already too late. You've already are headed in the wrong direction and down that path. Now, you could use a high-speed camera that's running 1,000 frames a second to see the flash, but you're also seeing the result of something that happened in the past. So by the time you're seeing it, it's already too late to react to it. So the camera methods really aren't fast enough to react to control what's going on. And also, if you can measure the flash intensity with a camera, it can't tell you whether a reduction in the flash intensity is because you're headed towards an open circuit or headed towards a short circuit. And that's what you need to know in order to know which direction to adjust the velocity. So a superior approach would be to use electrical parameters, because you could, let's say within a 10 millisecond time window, figure out what's going on with your flashing. Are you flashing right? Are you flashing too little? Or are you headed into a short circuit? Consistent high-intensity flashing, will have rapid flickering up and down voltages that are occurring, and you'll see corresponding rapid flickering down and up currents. And if the current rises are coincident with the voltage drops, because the voltage is what's creating your potential, and then if the current is drawing and it's going high, it's dragging down the voltage that's occurring, and that's flickering up and down. And that's basically the signal that you want to be seeing as you're running through your flashing process. Now, if you start to see the frequency of these voltage groups go down and the corresponding frequency of current spikes go up, you're headed towards an open circuit. So if you have duty cycle control, you want to be increasing your duty cycle to operate to compensate for that. If you're running with velocity control, then you want to speed up to start to get better circuit contact in order to maintain that flashing. And now on the other end, where you start to have a short condition, what you'll see is you start to have a sustained voltage drop without any glitches on it, and sustained intervals of current rise that are occurring, which means you're headed into a short circuit. Here also, on the velocity, you could see that the machine is having difficulty maintaining a consistent velocity, and actually momentarily stalled to zero when it was entering the short circuit condition, but managed to blow itself out and continue and regain flashing. So it's important to coordinate your duty cycle of applied voltage with the feed rate of the parts, and use speed control when the duty cycle isn't enough to maintain that flashing. So now this also requires a machine that's capable of producing repeatable motion, and you need to be, in order to make a consistent upset as you're entering into the upset part, and as we already discussed, having clamps that don't slip. And it also helps in order to know what happened afterwards to be able to monitor the upset pattern. And as we discussed earlier, you have to monitor the entire profile response, because monitoring final values alone isn't going to give you the entire picture. And here's the curve of, you're seeing the upset motion on the top. Each vertical bar represents 1 millisecond of time. So you actually reach final upset on this weld at about 25 milliseconds. You can see the velocity is rapidly rising to a peak and then drops off, and that's a profile that in this operation would consider to be a healthy result. Now, later in the afternoon, same job with this company Welding, we see this start to happen. And here's a case of, you see at the 25 milliseconds that you would expect your upset to have been completed, you actually have a lower than normal upset. The velocity never got up to full velocity, and you can see the velocity drooped just about to zero, but then picked up and started rising again. This is the signature of your part slipping in the jaws of the machine. And now, because your velocity is rising, the jaws are slipping, you're seeing your platen motion starting to rise off the scale there. And on systems that just look at the final platen motion to say I had good upset, they would interpret this as I had great upset, this is a great weld, when it's really an undersized weld that had insufficient upset, and they missed it because they weren't measuring the entire profile. Now, many of these flash welding installations, they have insufficient power to generate a consistent flash, because if you're running wide open on your voltage, and you're running with, if you have a system where you're using taps and you're operating, we run into installations where they're just line drops from the power company that mess them up, and they can't function during certain time windows. And the other thing that we see that's prevalent on these machines is the welding transformer saturating itself. Because a single-phase AC transformer, if you don't have a balanced signal on both polarities, the transformer saturates. And basically what saturation means is it causes the transformer to behave as if you took the iron core away from the transformer, it starts to look like a short circuit, which causes your primary current to shoot up very high and your secondary to dwindle to nothing. And this happens intermittently on and off throughout the entire flash welding process on a lot of installations because of the unbalanced signal being produced by the combination of the flashing and the SCRs that are firing them. So being able to manage that saturation and keep it from happening can be a major element in keeping the power requirements to the power company way down. Now, we already discussed about half cycles of SCRs being inefficient, and this is an example of a capable welder with an SCR-based control, with an incapable SCR-based control, yet it's a capable flash welding machine. And you could see that there was just intermittent flashing on and off all the time. This operation is plagued with never having quite consistent flash. And then they wonder why they can't control a consistent upset process, even though they're monitoring. Their monitoring is just, they really don't even need to monitor, because you don't need a monitor to tell this operation that they can't make two welds in a row that are the same. It's only an operation that actually has a consistent process where monitoring the process becomes important, because then it makes it very easy for them to identify when they have a problem. This is the conventional circuit arrangement of a system with an SCR-based control hooked to a single-phase power line. And so whatever current your transformer draws is coming directly from your power line. What we've seen is, you switch to inverter controls, you can reduce this power demand and increase the transformer efficiency at the same time while solving your problem of inconsistent flashing. Because you have a sustained peak voltage that you're applying consistently to the machine that you cannot do with an SCR-based control, and you can successfully use duty cycle control to control the flashing intensity. And then if you're using a single-phase AC transformer with your inverter instead of an MFDC, you can use adaptive control to dynamically balance the weld transformer to avoid saturation during the weld, and which is an important factor because MFDC transformers are even more susceptible to saturation than regular AC transformers. And if it's not a balanced signal going into them, then they go in and out of saturation very quickly and also cause very big current rises. So being able to just take a inverter system that hooks to a three-phase power line and hook it to the same single-phase AC welding transformer that you're used to using basically can transform your operation and significantly reduce the power consumption requirement as well. I know when we've had to grapple in some fleeting instances with power companies, we'll represent to them that we guarantee that your line current will drop to 82% of what your current used to be with an SCR-based control or better. And just from your equations of going from single phase to three phase, that's the case. When you layer power factor improvements and then improved flashing capability on top of that, you can see dramatic improvements that occur with that process. And in terms of MFDC versus an AC transformer, MFDC, it magnetizes the machine in the part. Transformer have diodes on the secondary that are susceptible to failure. You also have a voltage drop from the diodes on the MFDC, so that now reduces your capability to initiate flashing compared to an AC transformer with the same turns ratio. And the MFDC is more susceptible to saturation. Now, here you can actually see the saturation occurring on alternating half cycles of the input to the transformer, where the current is just shooting through the roof, and at the same time you can see coincident voltage drops dropping to nothing. And when those events occur, you start to lose your ability to flash, while at the same time your power consumption starts to shoot through the roof. Now, if you can balance that to keep that from happening, in this particular installation, the current draw is actually able to be kept to a third of what it was when you were ignoring the fact that it was going in and out of saturation, while at the same time deliver better flashing capability. And here was a case of, we had a company, they had a single-phase AC flash welder that was supposedly drawing 800 amps. The power company told them not to install it, that they don't have enough power to run this thing. And they didn't listen, and they went ahead and they put it in anyway, and they took out the fuses on the telephone pole and made the power company very unhappy. And the power company actually was very angry at this company and wanted to give them a bloody nose. They were telling them that it's going to cost them $250,000 to have the power feed that they need to operate this machine. And this fellow, Patrick C. McConaughey of Southern California Edison, said it negatively impacted the amount of voltage flicker experienced by customers connected to the 12 kV system to this welder. And we basically told the company that you can replace your SCR control with an inverter wave synthesis system, and we'll guarantee that it'll reduce your inrush current by 18% on that. And of course, it took a lot of posturing with the power company because they wanted to sell them this new power feed. But in the end, they reported that the new control reduced the flicker on the power grid to allowable limits. And in fact, the customer reported measuring only 107 amps power draw on each power line that had previously reported having a 1500 amp inrush. And that is largely attributed to the more efficient flashing, because when you're efficiently flashing, you actually use dramatically less current than when you're inefficiently flashing. And this was the actual machine that was the culprit in this situation.